Hi, we're going to go over writing differential rate laws in this video. So rate laws are something that we're going to use to show the relationship between concentration and the reaction rate. We're going to be focusing on the forward reaction, so we're just going to be looking at the concentrations of the reactants, not the products. All right, when you look at a reaction here, and you look at the rate law is always going to be written as rate equals K times the concentration of one of the reactants to some power times the concentration of another reactant to some power. Anytime you see brackets, the brackets represent concentration. You'll notice that these exponents that are behind it, those are going to represent the order of the reactants. And so I'll show you how to calculate and figure out what the order of each reactant is going to be. We have to look at experimental data to figure out what that order is going to be. The K is going to be some constant. All right, so when you write a rate law, you would always start by writing rate equals K, and then whatever you figure out from the experimental data itself. All right, so the exponents are going to be the order of each reactant. In order to figure out the overall order of the reaction, you would just add all of those exponents together. So when you look at this rate law here, rate equals K times concentration of A times concentration of B squared, the order of reactant A is 1 because there's no exponent. The order of reactant B is 2, and then the overall order is 3. So when you look at this, let me get my annotate tool here. Okay, so this here is your initial concentration of the reactant. So we would be looking to see what is happening to the concentration of the reactant. What are we doing to that? So that we can see what kind of effect it has on the rate, all right? And then just a reminder, what we saw in that last couple of slides is that the order is going to be the exponent, okay? So if your initial concentration is doubled and the effect on the rate is doubled, the exponent on the concentration would have to be 1. That's why it's a first order reactant, okay? Whereas if you look at this third line, for example, if you see that the reactant concentration is doubled and you see that the effect is 8 times, the exponent on that is going to have to be 3 in order to get 2 to the third power is going to equal 8. Okay, so we're looking to see what this exponent has to be in order to see that effect on the rate. So we're going to go over some examples here. All of these examples are going to be on page 3 in your packet. When you're trying to figure out what the order is going to be, you're looking at to find where the concentration of one reactant is staying the same, so you can actually see what the effect of the rate is on the other from the other reactant. So when you look at the concentration of A, you want to find where A is changing but B is staying the same. So between trials 2 and 3, you can see that between trials 2 and 3, the concentration of A is doubling and the concentration of B is staying the same. So whatever change is happening with the rate is because of the concentration of A. So we can see that the rate is quadrupling. So the exponent, the order on reactant A is going to have to be 2. So we know that rate equals K times the concentration of A squared. So then we want to look and see where, let me get my eraser here. So we want to look to see where B is changing, but A is staying the same. So between trials 1 and 2, we can see that A is staying the same. And what's happening with B? Well, B is doubling, so that's times 2. What's happening with the rate? It's also doubling. So what does the exponent have to be on the concentration of B? It has to be 1. So the rate would be concentration, rate equals K times the concentration of A squared times the concentration of B. And just like formulas and reactions, we do not write the 1. The 1 is understood. All right, so let's take a look at this next example here, okay? again, we want to find where the concentration of one thing changes, the concentration of the other thing stays the same. So when we look at trials 1 and 2, B is staying the same. So any change in the rate is because of A. So A is doubling. And what's happening with the rate? The rate is also doubling. So since it's both doubling, what does the order have to be on the concentration of A? The order is going to have to be first order. Okay. So down here we would say rate equals K times the concentration of A. Now we want to find where B is changing, but A is staying the same. So between trials 2 and 3, concentration of A stays the same. Concentration of B is tripling. What's happening to the rate? It's also tripling. So what does the exponent have to be up here on the concentration of B in order to have that effect on the rate? That has to be a 1. So we have concentration of B down here. Rate equals K times the concentration of A times the concentration of B. What's the overall order of this reaction? Overall order is 2 because we add the exponents together. Next example. Let's look at example 3. Okay, we only have one reactant, all right? If you see something that's in scientific notation, it might be hard for you to see exactly what's happening with the effect on rate. Because if you look at trials 1 and 2, for example, the exponents are changing here. So sometimes some people have a hard time looking at that. If you look at trials 2 and 3 instead, because the exponents are staying the same, you can really just focus on what's happening to the first number. Okay, or you can always put it in standard notation too in order to have a better idea of what's actually happening. But we can see that the concentration of A is doubling and the concentration, or the rate is quadrupling. So what does the order have to be on the concentration of A in order to see that effect on the rate? The exponent has to be a 2. So our rate law would be rate equals K times the concentration of A squared, all right? All right, so this next example, example 4, again, we want to look to see where the concentration of one thing is changing, the concentration of the other thing stays the same. So in trials 1 and 2, the concentration of A is changing, the concentration of B stays the same. So any change on the rate would be based on concentration of A. Well, A is doubling, and you can see when you look at the rate here, the rate doesn't change. So what that means is that changing the concentration of A has no effect on the rate. So that means A is not going to be written in the rate law. So now we can focus on B. So in trials 2 and 3, A stays the same and B is changing. So B is doubling. And what's happening to the rate over here? It's also doubling. So what does that exponent have to be on the concentration of B? It's going to have to be 1. So rate equals K times the concentration of B. And that's it. All right, so this time we're going to also go over how to figure out the value of K. All right. Before we start that, though, what I want to do is point out the units for rate. Okay, so the units for rate is moles over liters times minutes. That time can change depending on, what kind of trials you're running. So that could be it. But moles over liters, that represents concentration, molarity. Okay, that's how we calculated molarity. So that's why it's moles over liters times minute. That's going to be important when we're determining the value of K, or the units of K rather. So we have two reactants here. Again, we're going to be looking at where concentration of one thing stays the same, concentration of the other thing changes. So the NH4 plus 1 changes between trials 2 and 3, but the NO2 ion stays the same. So the change in rate has to do just with the ammonium ion. So the ammonium ion doubles, and we can see that the rate also doubles. So the order of the ammonium is going to be 1. So we have rate equals K times concentration of NH4 plus. So then let's look at, sorry, I gotta erase this. I can't erase all because then I'll erase all my hard work down there. So then we're gonna look at the nitrite ion. Okay, so in trials 1 and 2, the ammonium ion stays the same. The nitrite ion is doubling. And what's happening to the rate? It's doubling. So this is times 2, this is times 2. So what does the order have to be up here on the nitrite ion? It has to be times 2. Or sorry, times 1. Because the effect on the rate is the same as the change in the concentration. So when you determine the value of K, you just pick one row and you fill it into your written rate law. So I would pick the first, it doesn't matter which row, you can pick any row. So I would have 1.35 times 10 to the negative 7 equals, I'm going to be solving for K. I plug in my concentration of ammonium and I plug in my concentration of the nitrite. And I solve for K. And I don't have my calculator handy, so I'm going to go ahead and just pull up the answers here. So you can see that here, the units, or sorry, the value for K is 2.7 times 10 to the negative 4. The units, so because the units of the rate are this, in order to get that to be the units for K have to be liters over moles times minutes, okay? So the liters and the moles are gonna switch places. Now there's an easy way to figure out what the units are gonna be there. Units for K are gonna change depending on what your rate law is. So let's look at the shortcut of K. So first off, it's always gonna be liters over moles times time, whatever that value of time is, depending on what your experimental data says, okay? But there could be an exponent up here on the liters and the moles. And that exponent is going to be the same for both the liters and the moles. It's actually going to be one less than the overall order for the reaction. Okay, so you, again, to find the overall order of your reaction, you add your exponents together. And then you just subtract 1 to find the exponent for your K units. Okay, so if your overall reaction is the third order, then the exponent on the liters and the moles would be 2, 1 less than the overall order, okay? So, I want you guys to do some practice here. Page 4 and 5, you have some practice problems. You need to do as much as you can to understand how to do the work. And if you have any questions, just let us know. Good luck.